looking on a number of papers. I'm afraid that one seminar is not enough to cover that.
No, I'm not. I'm not going to cover any details. I would like to give a sort of an overview of what sort of mathematical topics come up in studying three-dimensional supersymmetric quantum field theories.
Okay. No, I'm just thinking about if there would be not enough time, you can continue maybe few time after a couple of weeks. Okay, let's keep it in mind.
I mean, yeah, if there are any topics that you find interesting, I can give a separate seminar or lecture of them. Next few weeks, it's fine. I mean, I hope it's okay. I'm not going to go into details in this overview.
Sure. How to make there is an echo because of YouTube. How to
just close that YouTube window or stop the video there.
say it again?
Can you just close that YouTube window?
I don't have a YouTube window on my.
But do you have your browser open now?
We did it. We're not in Switzerland, so our participants are not as exact as they should be. So
It's okay, it's okay.
And we don't have formal introduction of speakers, so you may start now. Oh, whatever it's convenient for you.
Okay, it's fine. Okay, so I would like to give an overview of some of the mathematical topics which occur when studying supersymmetric quantum field theories in 3 dimensions. This is a subject which has been a focus of my research for the last 5 years. It's a place where there are a lot of fruitful interactions between mathematics and physics at the moment, perhaps comparable to what was going on with mirror symmetry in 2-dimensional quantum field theory about 20 years ago or more. I don't know. Anyway, quantum field theory in general is a large and complicated subject, poorly understood both physically and mathematically. In a sense, we understand we feel we understand reasonably well some examples of quantum field theories, weakly coupled quantum field theories, for example, or perhaps some topological quantum field theories. But we're kind of lacking an overall understanding, global understanding of what quantum field theory is. Although perhaps there is some hope of improvement in that direction thanks to things like Bootstrap program. At the moment, we don't really know what the quantum field theory is in an abstract sense, or which sort of data do we need to give to really present a quantum field theory. Now, among the various examples that have taught us what a quantum field theory can look like, supersymmetric quantum field theories play a major role. So a quantum field theory in general has translation symmetry, meaning that the sort of quantities you can compute can be computed everywhere in space-time without changing the answer. A symmetric quantum field theory is a quantum field theory where you have an extra symmetry called supersymmetry. A Grassmann-Odd symmetry with algebra, a collection of Grassmann-Odd symmetries whose algebra closes on translations. Schematically, can you see my cursor?
Yes.
Can you see my cursor on the screen?
Yes.
Oh, okay, yeah. Excellent.
Maybe it will be also helpful if you have a file with transparencies, if you send it to the chat. And
okay, do you want me to send the transparencies to the chat now?
Yes.
Okay, let me see how do I do that. So which I'm not quite sure I know how to send it to chat.
The low part of the Zoom screen, you have probably chat, and you can.
File. Okay, I see it. Thank you. Okay. Very good. Sorry, I think I sent it only to Andrei by mistake. A second. Okay. Do you get it?
Yes.
Yes, thank you.
Okay. Very good.
So is it okay if I put it in the description on YouTube?
Sure.
Thanks.
Okay. So in a supersymmetric quantum field theory, there are these odd supercharges. I usually denote as Q. They might have they transform as spinors in space-time with anti-commute to translations, with some algebra with detail not important now. Now, supersymmetry protects some quantities in these quantum field theories and make them more computable. So that instead of there are some computations in supersymmetric quantum field theories, which instead of being complicated analytic problems, become algebraic problems. And so there are also places where you can find a lot of fun mathematical structures. Often these protected quantities can be captured by sort of simplified quantum field theories by a procedure called twisting. So the idea of twisting is quite simple. You pick one of the supersymmetry generators, which is nilpotent, and you add it to the BRST operator. In practice, you're essentially taking a cohomology of your original quantum field theory with respect to this odd symmetry. And as it often happens in cohomology, things simplify a lot, but you might still be able to capture some important information. For example, pretty recently, some protected calculations in three-dimensional quantum field theories were used to sort of as a seed to bootstrap other correlation functions of the actual physical theory. So when you do this cohomological operation, right, you throw away most of the dynamics, but not all of it. In particular, if you look at the supersymmetry algebra, you can see that once you treat one of the supercharges as a differential, many of the translation operations might become exact. Concretely, that means that if you do a calculation and you try to move around the local operators, your correlation function, the result might be an exact change, which goes away in cohomology. So these twisted supersymmetric quantum field theories are often topological quantum field theories, meaning the correlation functions do not depend, or BRST closed operators do not depend on the position of the local operators. Or sometimes, depending on the supercharge that you're using for the twisting, they might become holomorphic, meaning that perhaps the correlation functions depend only holomorphically on the position of the operators. So these twisted theories are self-consistent quantum field theories of cohomological type, which capture the protected properties of the original supersymmetric quantum field theory. Now, which kind of twists are available to you depends on which dimensions of what dimensionality for your space-time and how much supersymmetry do you have available. So if you work in 3 dimensions and you have the smallest possible amount of supersymmetry, which is called n=1 supersymmetry, where you essentially have only 2 supercharges, then there are no twists. Those supercharges are simply not nilpotent. So you cannot use them as a differential. If you have twice as much the amount of supersymmetry, something called 3D n=2 supersymmetry, then there is essentially 1 nilpotent supercharge that you can use. And if you twist the theory by the supercharge, you get something that is called holomorphic topological, meaning that out of the 3 directional space-time, 1 direction became topological, while the other 2 became holomorphic, meaning correlation functions of local operators do not depend essentially on the position in the z direction, and depend only holomorphically on the plane, on the remaining 2. Because of that, a lot of calculations can be done using essentially algebraic geometry. The sort of mathematical objects that appear in calculations are things like the fine Grassmannian, perhaps the block homology or some shifts on the fine Grassmannian. If you have more supersymmetry, which is sort of 8 supercharges, something which is called 3D n=4, then you have a variety of possible nilpotent supercharges you can use. Some supercharges give you topological twists, where correlation functions are independent of the position of local operators or the metric on your space-time in all directions. There are 2 such twists. One is called the A twist, and the other is called the B twist. And then there is still the original holomorphic topological twist, except it now has some sort of a residual supersymmetry, some extra odd supercharges which survive the twist. And a very useful perspective is that one can first deform to the holomorphic topological twist and then use the residual supercharges to deform further to the topological twists. Think about a sort of a spectral sequence where you're trying to compute the rank homology, and instead you compute first the block homology, and then you take the cohomology of del to get to the rank homology. This is interesting because although what you want to compute is topological, if you compute it passing through the holomorphic topological twist, you will again be able to use complex analysis, algebraic geometry. So that's the reason algebraic geometry is playing a very important role in the study of these 3-dimensional twisted theories. And so again, you'll have calculations which involve things like the fine Grassmannian. Perhaps a bit of an analogy here would be that it's like studying a space of flat connections by identifying them with the modules or perverse sheaves. You use complex analysis to study something which is ultimately topological. Are there any questions before I continue? Okay. So when I say that these theories are topological, yes, was that a knock? No, sorry. When I say that these theories are topological, what I mean is that they are topological in cohomology, meaning that if I sort of change the location of a local operator, or I try to change the metric, the answer changes only by terms which are exact in cohomology and go away in the final calculation. When you have this sort of cohomological topological field theory, the mathematical structure that you find is an EN algebra, where n is the dimension of space-time. So in these A or B twists, you find that the local operators form what's called an E3 algebra. So what does it mean? It means that I have some space, some vector space of local operators, which are sort of the questions I can ask at a given point in space-time. And then these local operators can be moved around quite freely up to homotopies. And they can be collided. And the collision will be associative, again, up to homotopies. And because I can bring the operators together from various directions, it will be commutative, again, up to homotopies. These homotopies are captured by Hager operations, which altogether form this E3 algebra. So if you're familiar with the language of factorization algebras, this would be just a topological factorization algebra in 3 dimensions. Or perhaps in the language of operads, this would be an algebra modeled on an operad of little cubes or little balls in 3 dimensions. So in practice, at least when these algebras are localized in degree 0, which is what happens typically for these 3-dimensional twisted quantum field theories, what you get is a commutative algebra equipped to the Poisson structure. This Poisson structure somehow it's a remnant of these Hager homotopy operations. You can often think about this algebra as an algebra of holomorphic functions on some complex symplectic manifold called the space of vacua. So the notion of vacuum in a quantum field theory is quite straightforward. It's sort of a choice of a value of an expectation value for all the operators of your theory. And in this sort of topological context, it becomes sort of a map from your algebra to the complex numbers, which is compatible with multiplication. So you get the space of vacua, sort of the spectrum of this commutative algebra. These spaces of vacua are called Higgs branch or Coulomb branch, depending if you're working with the A twist or the B twist. So when you hear somebody talking about the Coulomb branch or the Higgs branch of some 3-dimensional N=4 theory, you can think about them as the sort of the thing that tells you which local operators you can find in the A twist or B twist of the theory. So to this holomorphic symplectic manifold, whose functions are the local operators in this theory. One thing I should mention is often useful to employ something called an omega deformation, which essentially corresponds to working equivariantly in the plane. It's like instead of doing cohomology, you do equivariant cohomology using the symmetry of rotations around the plane. The effect of this is essentially to force your local operators. Yes?
I'm sorry, who is the plane here? I mean, I'm saying equivariant with respect to the plane is...
Sorry, we have R3, and when I say plane, I just mean an R2 inside R3. So take the cartan of SO3. You have a rotation, an SO3 group of rotations of R3. You can take the cartan generator and work equivariantly with respect to that.
So it means that you're actually rotating R3, no, not
yeah,
R3.
you're rotating 2 of the R3, but essentially one of the directions in R3 is not rotated, right? And the other 2 are. So this is particularly compatible with the holomorphic topological twist. Then when you do the omega deformation, you're using the holomorphic direction. And
is it the same case as when calculating Nekrasov's partition function from 6D to 4D?
I would have said that it's the same thing that you do when you compute Nekrasov partition function in 4D to reduce it to something 0-dimensional, or right. So if you are in R4, you can use an omega deformation in using the generic element of the Cartan, and this will force local operators to live at the origin of R4. That's the context of sort of Nekrasov calculation, original calculations. If you do this to a 6-dimensional theory, and you only use rotations which rotate R4 and preserve the whole R2, then you can go from 6D to 2D, and you will get some depending on the 6-dimensional theory, you get some chiral algebra. But I can discuss this perhaps later. Here in this 3-dimensional context, the effect of this omega deformation is that it sort of kills 2 of the 3 directions. So everything lives in one direction. You get an E1 algebra, a non-commutative algebra of operators colliding along the 3rd direction.
Sorry,
Do you have just a single epsilon parameter which
Yes.
becomes a Planck constant below?
Yes. That's right. So this deformation is a modification of the theory, so it modifies the algebra of local operator. Instead of having a commutative Poisson algebra, you get a non-commutative algebra, which is the deformation quantization, pretty much. Well, it's the quantization of the original algebra, where the quantization parameter is this deformation parameter. Yes?
Sorry, maybe the next question was the following. So, omega deformed 4D theory can be obtained as a reduction from 6D theory with some special boundary conditions, like rotation by an angle proportional to the compact dimension angle. So, can we do the same construction for this 3-dimensional omega deformation?
So let me see if I understand correctly. So one way to understand the omega deformation is the following. You can take your 3D theory and sort of try, if you have a Lagrangian at least. So the omega deformation is a notion that does not require a Lagrangian. But if you do have a Lagrangian, then what you can do is to sort of try to write down a 4-dimensional Lagrangian, whose dimensional reduction is your 3D theory, and then compactify this 4-dimensional Lagrangian on a circle while rotating the plane as you go around the circle. This is how Nekrasov introduced the Nekrasov background originally. And then this reduces back to 3 dimensions, but the theory is modified. And this is the omega, one way to think about the omega deformation. But mathematically, just really working equivariantly with respect to rotations.
Thank you.
Right. Okay. So this gives you a sort of canonical quantization of the algebra of functions on these Higgs and Coulomb branches. And although this perspective might seem very far from the actual physical theory, because we went to the twisted theory and then with the 4 we turned on omega deformation. It turns out that this algebra actually captures important information of the original physical theory. So for example, when you compute correlation functions or the physical theory on a sphere, which preserves some amount of supersymmetry, it turns out that you get an OP, when you bring operators together, you find exactly this quantized algebra. And so actually this quantized algebra inherits a lot of funny properties from the unitarity properties from the physical theory, such as the existence of a trace with certain positivity properties. But I will not discuss it now. But just to say, so this abstract construction really carries important information for the physical theory that then can be actually fed into bootstrap procedures, which can give information even about the non-supersymmetric operators of the theory. So this is physically important. Now, there are a lot of 3-dimensional N equals 4 theories, we don't know most of them. The ones we know are most of the ones we know are sort of standard gauge theories. They have a Lagrangian, where there are some gauge fields and some matter fields. And the gauge fields are, the whole Lagrangian is captured once you tell me a choice of a gauge group, which is some reductive group G, Lie group G, and a symplectic representation, which I'll call R, which sort of controls which matter fields you put in your theory. Then the Higgs branch of this gauge theory has a straightforward description. It's just a symplectic quotient of R by G. Or if you turn on the omega deformation, it becomes the quantum Hamiltonian reduction of a Weil algebra based on R. So that's pretty straightforward, well understood for a very long time. The other branch of gauge theories is much more subtle. A physical description of the Coulomb branch was lacking for many years, except in specific examples. So in specific examples, one could use string theory or guesswork to figure out what the Coulomb branch would look like. But there was sort of no general understanding of what the Coulomb branch would be. Essentially, the reason is that the local operators which whose expectation values parameterize this Coulomb branch are not just polynomials in the elementary fields of the Lagrangian, but they're disorder operators, something called Dirac monopoles. And when you try to figure out what happens when you collide Dirac monopoles, you need to understand, you need to do some semi-classical calculations which involve very singular spaces of field configurations. And so here is a place where we first saw the power of algebraic geometry in studying this sort of twisted theories, because of the BFN construction. So Braverman, Finkelberg, and Nakajima figured out how to give a definition of the Coulomb branch, a mathematical definition of the Coulomb branch, in terms of the equivalent homology of certain spaces close to the Fein-Grassmannian. And so they managed to sort of tame the singularities implicit in these Dirac monopole calculations. And a very interesting feature of this is that the calculation is really, right, it's based on algebraic geometry and presumably is implicitly based on this sort of path to the topological theory, which passes through an holomorphic topological twist. Now, a full derivation from, as I said, this is a semi-classical calculation. So it should be possible to really prove that this is the correct answer for the quantum field theory in this sort of twisted formalism. I don't think this has been done yet, but it should be doable. In any case, there is a sharp mathematical definition, which means that the Coulomb branch is something that mathematicians can talk about. And often these Coulomb branches are interesting spaces for geometric representation theory. So the fact presenting them as Coulomb branches seems to endow them with interesting properties. But for me, right, the lesson was that algebraic geometry really rules, that I need to understand these sort of things like the Fein-Grassmannian in order to study twisted three-dimensional supersymmetric gauge theories.
Sorry, is it clear why this algebraic geometric construction is related to the physical theory?
Well, I think you can get pretty close to it, at least, in the sense that it should be possible to, describe in detail the factorization algebra. Okay, let me try to say this correctly. So classical quantum field theory is now mathematically pretty well understood in terms of derived geometry. And semi-classical calculations are just classical quantum field theory together with geometric quantization, pretty much. So I think that a question like what's the space of local operators in a given quantum field theory, semi-classically at least, it's a question which can be addressed in a mathematically rigorous way at this point. and also what the OPE of such operators is in the topological direction should be something that can be addressed in a rigorous way. And if done properly, it should reproduce the BFN construction. Does this answer?
Yes. Thank you.
So now, right, understanding this properly probably would require understanding a little bit better what the holomorphic twist looks like mathematically. So abstractly is a factorization algebra, which is topological along one direction and holomorphic along the other two. So in principle, you know, you sort of know which mathematical object you're talking about. It's something, so some operatic object associated probably to something like the Dalbach homology of the configuration space of small cylinders in R times C. So there will be some composition of operations which sort of are topological along one direction, holomorphic along the other, and there will be some higher operations. So it's some sort of hybrid object, which is maybe something like an E1 algebra in chiral algebras, or a chiral algebra in E1 algebras. I don't think it has been studied in detail, but again, it should be doable. And you know, once all these higher operations are understood and possibly computable semi-classically, it should be possible not only to recover PFN, but also to give a direct derivation of a whole collection of mathematical results, which go under the general moniker of symplectic duality. So symplectic duality is a collection of mathematical statements which relate properties to the Higgs and Coulomb branches of a given 3D n=4 theory. One of the manifestations of this symplectic duality is the causal duality between the category O's associated to the quantizations of the Higgs and Coulomb branches.
Question, David. Question.
Yes.
So if you look at the Higgs branches defined on your previous transparency,
yes,
that is actually exhibits as a certain quotient. That's important because you can write many different spaces as different quotients, and this will be different things in this. Whereas the BFN construction, that really just gives you a singular space. It doesn't give you as a quotient.
That's true.
You know, once you start comparing, that poses difficulties. Do you see a way to upgrade or downgrade one side or upgrade the other side? Because as presented, there's the level of the output is different on two sides.
No, I don't think you should. Well, okay.
I can suggest an answer, but I don't know if I should do it now.
They are both E3 algebras, right? And there should be both deformations of this holomorphic topological algebra.
No,
makes them analogous.
In physical language, I think you should consider S-dual rather than mirror dual to this thing. And so, in other words, you get a space with the actual reduction of that. But I think that the space with G-check action is sort of the thing which carries the full information. But okay.
Well, one thing I would like to say is that, right, so this symplectic duality statement should not be only about gauge theories. And definitely should not assume the existence of a mirror gauge theory for which the role of Higgs and Coulomb branches are changed. So symplectic duality should be true for theories for which the Coulomb branch is not a quotient. Should even be true for theories for which neither the Coulomb branch nor the Higgs branch are quotients.
No, but David, I'm saying the singularity itself and the singularity written as a quotient are two different things. If you compute your things for two different, you take the same singular space, you present in the quotient two different ways. You compute with it, so that you get different answers.
You also get the same quantized algebras?
No, you get different theories if you write the same space written as
because it's not about spaces, it's about theories. Symplectic duality is a statement about 3D unequal for theories.
That's right. That's what I'm trying to say, is that if you
yes.
the BFN construction just gives you a space, as far as I understand, doesn't exhibit it, doesn't somehow exhibit it, the singularities coming from a quotient, any other.
And it shouldn't, because it might very well not be a quotient. There is no guarantee that you have a mirror theory such that the Coulomb branch of the original theory is the Higgs branch of the mirror theory. That's an accident. So, yeah, it's just an accident. So there's nothing intrinsic about the existence of mirror theory. So, anyway, unfortunately, we don't know how to write many unequal for theories which are not standard gauge theories. We do know some built as Chern-Simons theories. Nobody has yet done the localization calculations needed to figure out what the Higgs branches and Coulomb branches of those theories are. But they're presumably not quotients, neither of them. So there is, I'm kind of hoping that somebody will do that at some point. If possible. But also, right, another thing that sort of I would like is that perhaps if one understands this whole structure well enough, one can predict the existence of 3D unequal for theories which we do not know about. So I definitely don't want to live always in the world where the Higgs branch is a quotient. I would like to know what's the most general structure we can encounter. So notice that, right, a lot of the ingredients that go into symplectic duality are really weird from the point of view of the twist of the sort of Higgs branch and Coulomb branch as independent objects in a sense. For example, this Koszul duality I mentioned between category O's require you to somehow take a category of modules for the quantized algebra of the Higgs branch or Coulomb branch, introduced by hand an extra grading, and then apply Koszul duality, which sort of exchanges this grading with the cohomological grading. And these sort of structures seem pretty natural to, from this perspective. For example, the operator algebra of the holomorphic topological theory automatically has two gradings, turns out. And this sort of twists to A and B break one of the two gradings. So presumably some of the topological mathematical operations that go into symplectic duality are about, attaching some category O to the A-twisted theory and then somehow upgrading it to some category which has to do with the holomorphic topological theory, and then comparing it to the upgrade of the B-twist side. And I think it would be really nice to understand more carefully what's happening. So it should be possible to sort of have some general theory where you have this E1 algebra of chiral algebras equate with some extra supersymmetries and true topological deformations of that. And then you should be able to derive a universal Koszul duality statement which applies whenever you have this underlying structure, without ever mentioning, R over G or quotients or Higgs branch or BFN or anything else. And then when you apply this to the E1 chiral algebra associated to the gauge theory, you will recover the BFN versus R over G case. Any questions? Okay. Let me see how I do it time. Okay. So now, until now, I've been talking a lot about local operators, which are sort of questions you can ask about the theory at a point in space-time. The idealization of some kind of a probe or detector that lives in a small, or a lab that lives in a small region. But there is a lot more in quantum field theories than local operators. In particular, there is a very important notion of extended defect which is a modification of a quantum field theory along a whole submanifold in space-time. Whenever you have this sort of defects in a quantum field theory, you get a lot of extra structure going along. For example, there are the list of questions you can ask in the neighborhood of the defect is different from the list of questions you can ask away from the defect, which means that there is a space of local operators on the defect, which is different from the local operators away from the defect. And you get all sorts of operations where, you bring an operator away from the defect to the defect, or you multiply operators along the defect, or you perhaps build a sub-defect inside the defect. So you get a whole hierarchy of structures, which is sort of a quantum field theory within quantum field theory. And a lot of these constructions might possess a supersymmetry and survive the topological twist. So you'll find them in the twisted theories too. In the topological setting, sort of topological non-cohomological setting, this is what's called extended topological field theory. Let me give an example of the sort of structures which appear when you have defects. Suppose that you're looking at line defects, which are modifications of theory along a line. So these line defects support a certain space of local operators. And we're going to think about these local operators as an analog of endomorphisms of this line defect. Essentially, because if I have two local operators along the line, I can compose them. And if I can think about if I have two different types of lines, here a red line, a blue line, I can consider operators that live just at the junction between the two lines and behave a lot like morphism from a line to the other. Because, for example, I can do composition. If I have three lines, if I have an operator that changes one into the other and then changes another that changes the second into the third, I can compose them into an operator that changes the first line into the third. So typically, whenever you have lines, topological lines, you don't just get a space of local operators. You get if you think about the lines as objects in some category, then the local operators give you morphisms for this category. So when you have lines, you get categories, or perhaps in a cohomological setting, E1 categories, or A infinity categories, depending on what your presentation, preferred presentation. So, right, a lot of mirror symmetry, two-dimensional mirror symmetry is about, for example, boundary conditions in two-dimensional supersymmetric theories. And you get all sorts of A infinity or E1 categories of boundary conditions. If you have interfaces in two dimensions, which sort of where space-time don't end, but you have an interesting theory on both sides, then these categories get an extra structure of an extra monoidal structure. Essentially, you can take two lines and bring them together. If your lines live in three dimensions, you get some braiding too. You get braided monoidal categories. But you can also look at defects which are dimension higher than one. So you can look at boundaries or interfaces in three dimensions. And you start seeing things like two categories. So in this A and B twist, I will end up having ultimately some two category, some some homological version of a two category. In the holomorphic topological twist, is a little bit less clear what I get, but I will discuss it momentarily. Now, let me just repeat something that I already anticipated before. Which sort of computational tools do you have to address these questions? Are these physical or also mathematical questions? So, and in these twisted theories, a lot of the calculations are semi-classical. So if you understand your classical quantum field theory well enough, using perhaps derived geometry, and you understand geometric quantization at a categorical level, then you should be able to compute these quantities in a mathematically rigorous way. And if you have some underlying holomorphic setup, you can probably use algebraic geometry in the process. Now, an interesting feature is that often the same theory might have different semi-classical descriptions. So these are what dualities are. Dualities are typically non-trivial identifications of naively distinct weakly coupled theories. And when you do calculations for true dual theories, the protected data that you obtain must coincide. And so whenever physicists have guessed some dualities in the past, you can probably derive the whole collection of conjectures relating different looking mathematical objects. After all, I mean, this is sort of analogous to what happened in two-dimensional mirror symmetry. In two-dimensional mirror symmetry, right, you typically had two different weakly coupled descriptions of the same two-dimensional quantum field theories, and you derived non-trivial identifications of categories, like Fukaya category versus derived category of coherent sheaves. An important ingredient in these sort of ideas is the notion of Gflow. So in the physical theories, the action of scale transformations is very non-trivial. The same quantum field theory might look very different at different scales. So the Gflow is the effect of the scale transformations, and it can relate very different looking theories. A lot of theoretical physics is about finding what the Gflow does. So a lot of questions in theoretical physics are about having a microscopic description of a theory and trying to figure out what happens at large distances. And so any quantity which is invariant under the Gflow is particularly useful. And often these twisted theories are invariant under the Gflow. So a lot of these calculations in twisted supersymmetric quantum field theories capture information about their Gflow, which would be otherwise unavailable. And again, whenever you can predict what was the endpoint of an Gflow, you can derive some interesting mathematical conjectures if you can compute protected quantities at the beginning and at the end of their Gflow. So before when we're discussing before Higgs branches and Coulomb branches, we mentioned the notion of mirror symmetry. Sometimes you can find different gauge theories which flow to the same quantum field theory in the infrared. But perhaps what was the Higgs branch of one of the theories becomes the Coulomb branch of the other theory. And so there's this idea that often these Coulomb branches happen to look like Higgs branches of other theories, and vice versa. But that doesn't have to be the case. There is no reason for which, given a gauge theory, I should be able to find another gauge theory which flows to the same theory after exchanging Higgs and Coulomb branches. Okay, I might have been going a little bit too fast, but anyway. So using, right, and all of this notion of Gflow and duality is also applied to defects. So you can ask what happens to a theory after Gflow. You can ask what happens to a specific defect in the theory after Gflow. Or if I have two theories which are related by duality, I can ask what defects of the first theory are related to which defects of the second theory. Now, using defects, you can also relate problems in 3 dimensions to problems that occur in other dimensions of space-time. Now, you're probably familiar with two-dimensional mirror symmetry, which is something that has to do with two-dimensional theories with 2,2 supersymmetry. There is a very nice interplay between two-dimensional mirror symmetry problems and 3-dimensional n = 4 theories. Whenever you have a two-dimensional theory which has a G-symmetry, you can promote it to a boundary condition or interface for a 3-dimensional gauge theory with G gauge group. And this sort of promotes A and B models to E1 modules for the 3-dimensional theories. So if you're doing let me go back here. So if you had been studying theories in 2 dimensions with 2,2 supersymmetry, you would have a very similar picture. There would again be an A twist, a B twist, and an holomorphic twist. Now in two dimensions, so you don't have the sort of topological third direction. And you'll be able to study the A or B twist as deformations of the holomorphic twist. When you put these two-dimensional theories at the boundary of a 3D theory, you are sort of replacing the R factor in the geometry with an R plus, with a semi-infinite line. And so you can think about having operators in the bulk and bringing them to the boundary, or colliding with them with operators on the boundary. So the effect is that whenever you have some kind of E1 structure in the bulk having to do with the multiplication along the topological direction, now you get an E1 module for that E1 algebra. So if you're working the holomorphic topological twist, the sort of the two-dimensional chiral algebra, the two-dimensional holomorphic theory will be an E1 module for this E1 algebra of chiral algebras. And if you're working the topological setup, the E2 algebra of local operators at the boundary become a module for the E3 algebra in the bulk. And so, for example, there's been some nice work by Telemann, which allows one to understand certain structures which occur in two-dimensional theories with G-symmetry in terms of the Coulomb branch of three-dimensional theories. Now, another interesting connection has to do with 4 dimensions. You can promote the three-dimensional inequals for theory themselves to boundary conditions for a 4-dimensional theory. Now, the topological twist of 4-dimensional supersymmetric theories is connected with the subject of geometric Langlands in mathematics. So this sort of physical connection ends up drawing bridges between symplectic duality and geometric Langland duality. These sort of twisted 3D theories produce objects in the categories for geometric Langlands. And this is very useful perspective, both in understanding 3-dimensional theories and in understanding geometric Langlands, I think, in the sense that these constructions can give you nice examples of objects in geometric Langlands which are related by geometric Langland duality, or at least conjecturally. So, okay. Any questions? Okay. So let me tell you a few more things about the role of holomorphic objects. So when you study the holomorphic topological twist in 3 dimensions, the boundary conditions are also naturally holomorphic. Funnily enough, it's also possible to have holomorphic boundary conditions for when the bulk is topological. So it's possible to have a situation where the correlation functions in the bulk are topological, but correlation functions on the boundary depend holomorphically on the positions. So you can have a situation where you have boundary local operators which form a chiral algebra, while the bulk local operators, the bulk theory is topological. This is somehow analogous, yes?
Can I ask you, when you say there is a situation, what do you mean? The word situation means what?
It means that there are, pairs of 3D theory together with the boundary condition.
So it's a choice of boundary condition. Situation
Yes.
is boundary condition. Okay.
That's right. So there are all sorts of boundary conditions in the physical theory which preserve different amounts of supersymmetry. And some of them might end up being topological after the twist. And some might end up being holomorphic after the twist. even if the bulk theory is topological. And they are both interesting, right? If I have a topological boundary condition for the topological theory, I end up getting and perhaps I omega the form, I end up getting an E1 module for the quantized algebra of functions on the Higgs-Coulomb branch. And so that's perhaps a route into symplectic duality. On the other hand, if I have a holomorphic boundary condition, now I have some pretty rich structure on the boundary. I have a whole chiral algebra at the boundary. And now there is an interesting question of sort of what's the relation of that chiral algebra with the bulk topological field theory. For example, this chiral algebra must be, in a sense, still any one module for the, well, okay, there must be a sense in which the E3 algebra in the bulk can act on this chiral algebra. So with Kevin and Thomas Kretzig, we had some conjectural statements such as the algebra of local operators in the bulk could be the endomorphisms of the vacuum module of the chiral algebra. But there is still quite an amount of work to do there, even just to understand where the symplectic structure comes from that perspective, the Poisson structure, sorry. Anyway, so a good analogy for the situation is Chern-Simons theory. In three-dimensional Chern-Simons theory, you have a topological bulk, but if you try to put a boundary condition, you end up with the WZW model, the chiral algebra. And there is a deep relation between the WZW model and the Chern-Simons theory. For example, the category of modules for this chiral algebra is closely related to the category of lines in the Chern-Simons theory. And we expect something like that to happen also in this cohomological setup. So the three-dimensional topological field theory should control the category of modules for these chiral algebras. And these chiral algebras are often interesting logarithmic chiral algebras, which are very interesting subject to mathematical study too. And so these sort of statements can give you an analog of the statements relating the Kazan-Lustig category or the quantum group category to the WZW models.
Sorry, when you say that the 3D theory is supposed to control the category of modules over chiral algebra, so say that this chiral algebra depends on the choice of boundary condition. So
yes.
Are you implicitly saying that the corresponding category of modules will be independent of the boundary condition?
Possibly, yes. Or at least there will be a functor with sufficiently good properties from some category attached to the bulk to the category of modules.
Okay.
And here we're right. I do not know exactly if this functor is supposed to be an identity or not. There are some in examples. I mean, there is also the question of defining the correct categories on both sides. You know, when I say modules of the chiral algebra, which module am I talking about? Am I talking about Highest-weight modules or relaxed tightest-weight modules? You know, when you try to go into details, there are a lot of subtleties on both sides.
But as a first approximation, you're trying to say that the category is more or less independent of the choice of boundary conditions.
Yes, yes, that's right. And right, so this sort of statement should be useful in both directions. You know, I can imagine situations where I understand well the chiral algebra, and this allows me to compute the bulk category, or situations where understand the bulk category tells me something new about the category of modules on some logarithmic chiral algebra. Now, in fact, it's usually I'm particularly interested in situations where perhaps I know the chiral algebra, but the bulk theory was unknowable, meaning that I had a situation where the bulk theory was not a gauge theory, so I couldn't quite do a BFN calculation or a Higgs branch calculation, but perhaps I had some reason to guess the correct chiral algebra at the boundary, and then this allows me to compute properties of the bulk theory too. or perhaps, it would be interesting to know which chiral algebras admit a nice E3 algebra action. The whole holomorphic topological versus topological and holomorphic factorization algebras, I think, deserve to be looked at carefully. Okay, actually, sorry, I'm done with slides and with the talk. Do you have any questions?
Can I ask a question?
Mm-hmm.
Can I ask? It's going back to the local operators and symplectic duality.
Yes.
So first, so Nadler and Ben-C had some nice kind of proposal to relating this causal duality in the original context, to maybe generalized in a different way, to local geometric Lagrange by taking S1 localization, S1 fixed points on both sides. Does this fit into this story? I mean, because
yes, I mean, right. So I was saying you can promote three-dimensional theories to boundary conditions for dimensions. So local geometric Lagrange is about studying 2D objects in the four-dimensional theory. So you get a two category associated to two-dimensional objects in the four-dimensional theory.
And then
is what you,
some sort of what they call S1 localization can be.
Right, that's right. So if you sort of, there is a two category attached to a circle. And this is what associated to surface defects in four dimensions. You can consider surfaces that end at the boundary. So this tells you that the boundary condition attaches to the circle a category inside this two category. So objects, some of the objects in this two category are associated to boundary conditions, to three-dimensional boundary conditions.
So their approach is quite general. So, I had another question. So another feature of this. So you mentioned this feature of causal duality, but like another feature that, in particular, like Andrei Okrenkov worked out is the relation, like the equivalent quantum K theory.
Yes,
should be the
that's
same
right.
for the two dual sides. Is there a way to relate this to facts, like maybe as a some generalization of causal duality, which can be thought of as categorification of quantum K theory? Because
so physically, the statement should concern the compactification of the 3D theories on a circle. That's what.
So that would be the category.
That would be K theory. What equivalent K theory should be. So it has also something. Okay, sorry, but a direct relation to symplectic duality is not so obvious, in the sense that symplectic duality, I think, has to do with modules for the algebra. So it has to do naturally with boundary conditions, but right, and so it would have to do with segments rather than circles. So that makes it a little bit difficult to. Well,
Sorry, can I say again? So I said that quantum K theory is supposed to be what? I mean, quantum K theory is a vector space. Right? So this vector space is supposed to be what?
It's a vector space. That's right. Okay, let me say first of all what the equivalent cohomology is supposed to be.
Maybe I say it's not a vector space.
Well, in particular, it's a vector space with structures. I mean,
Right.
It's a vector space, not a category. It's a vector space in this sense.
Right. So I think about equivalent quantum cohomology in 2D as having to do with the omega deformation. So I do omega deformation of the 2D theory, and so now operators live only at the origin, have a vector space.
Wait, but this is equivalent quantum cohomology of what?
Of some, of of a space. I'm sorry, right? I've current homology of some space or some quotient maybe, and I can build a sigma model into that space as a two-dimensional theory. Then I can omega deform it.
Okay, but this is about two-dimensional theories.
Yes, that's about two-dimensional theories. Now, if I have a three-dimensional theory, I can compactify it on a circle, and then it looks like a two-dimensional theory. And this is what a covariant K theory should be.
Wait, but if you start, say, with a gauge theory, I was saying that somehow.
Can I intervene for a sec? So if you have a three-dimensional theory, like David says, you can consider a time circle. So you're going to get some kind of index on the moduli space of all possible surfaces with all possible marked points. That's like a K theory class on, whatever, like Riemann surfaces with marked points and with some insertion, some operator insertion with marked points. And that K theory class, you can say that K theory, that kind of K theoretic topological field theory is the quantum K theory. You can say it like that.
Quantum K theory of what? Sorry, you didn't say. If you start
of your, I mean, it's like one manifestation of you had some three-dimensional theory. You can consider that theory living as on some kind of circle bundles of Riemann surfaces, and then you're gonna get then your quantum K theory is gonna give you an element of K theory of the moduli spaces of all possible Riemann surfaces with all possible insertions. And this is the object we're talking about.
No,
you can also take boundaries. Then it gets a little more complicated, but in principle, this is already reaching out. Yeah.
But I think the examples that's equal to quantum K theory of either Higgs or Coulomb branches. They're
equal. You have two kind of two K theory classes on the modular of Riemann surface, and they're equal between two dual theories.
Yeah, well, something I could say is that a covariant K theory is something I can consider for 3D n equal 2 theories already. I don't need to have 3D n equal 4.
That's true. Yeah. Somehow, if you.
So it's a nice intrinsically holomorphic topological object.
Yeah. And if you're going to bring surfaces with boundaries, this means you're also going to get like formal formal disks around marked points, and even that is supposed to be the same. So
yeah, but that will be problematic a little bit, right? Because if I want to work holomorphically, it's very hard to put actual boundaries.
No, but let's say you put formal boundaries. You take like formal partial
disks. That's right. Which essentially means having line defects. So
no, that would be already if you take that would be already, this would be like a surface defect, but in some kind of Q expansion. This would be, you imagine you have a surface, but the modulus of that surface is near 0.
Yeah,
that's...
Right. So I do not know. It might be possible to connect this to symplectic duality using the truth. I'm not sure, but it should be possible. Another thing you could do would be to sort of try to replace the circle with a segment. Sort of put your boundaries in time. I'm not sure to how K theory plays with that.
Sorry, I may have missed the beginning of your answer because my internet connection failed. But going back to this categorification question. So what is your proposal? To sort of, so causal duality is some relation between categories, and then
yes. Well, so I would
is a relation between something which is not a category, whether it's a vector space.
Well, no, I would say, okay, suppose I have this E1 algebra of chiral algebras, which comes from the holomorphic topological twist. And then I can think about a category of E1 modules, E1 chiral modules, E1 modules in chiral algebras for this E1 algebra in chiral algebras. That, I guess, would be a category, right? And these would be boundary conditions in the holomorphic topological twist. And I think this category is hopefully the enrichment by the extra grading of the category O's for the Higgs or Coulomb branches.
I think Roma's question was about how this Cazul duality statement is supposed to be related to the statement about quantum K theories.
Ah, sorry, no, that I don't know. That I don't know. So well, except that, you know, again, abstractly, once I understand this E1 algebra of Carl algebras, presumably I can think about the K theory of it. So there should be sort of abstract way of taking factorization cohomology on a Riemann surface and then taking K theory of that. It should be an operation I can do just on these E1 algebras or Carl algebras, without reference to a specific manifold or, you know, to a specific gauge theory.
But I think that this is supposed to recover the quantum key theory.
Yes, yes, that's right. So I think there is just this holomorphic topological factorization algebra, and you can do things to it.
So again, the structure is that you have this E1 algebra in the category of chiral algebras, and I'm saying that you can apply some formal procedure to it, which in these examples will produce the quantum K theory.
Yes.
Okay, but you don't know how to say this explicitly.
Well, can I say I take factorization cohomology on a Riemann surface that gives me a E1 something, and then K theory of that?
Maybe.
Yeah, I don't know. You shouldn't ask me for the mathematical formalization. But you know, the intuition should be clear. I had this holomorphic topological object, and I ask what does it attach to a circle times Riemann surface, and that should be the quantum K theory of the manifold. And if you have two mirror theories, which should give you the same holomorphic topological objects, they'll have to give you the same answer.
Okay, if there are no more questions, I should ask the traditional question, who's going to join us for dinner? Unfortunately, these days, it's a senseless question because of time difference. So let's postpone this question till the actual visit to Skolkovo. So thanks a lot for your.
Thank you.
Bye.
Bye.